Okay, hello everybody, and welcome to this talk on exploring the scope and educational value of frequency recognition on the Microbit V2. And as you very kindly mentioned for me, that's actually just a huge mouthful to try and make my dissertation sound more interesting. So in simple terms, we're basically looking at can you recognize musical notes on a Microbit V2 and how sound as a whole can enhance learning with the Microbit. Okay, so how did this work kind of come about? I'll give you a bit of a background first. This work was done as part of my master's course in computer science at Lancaster University. And during that course, you undertake a 10-week work placement. And I did mine with, of course, the amazing Microbit Foundation, who are great partners with the uni. And during that time on placement, I was looking at ways to improve the current sound capability of the Microbit, especially sound output. And that's kind of a theme that I took into my university dissertation, which was about 10 weeks. And that's the kind of work I'll be focusing on today and to see where that kind of led me for my dissertation. Okay, so the first question is, or kind of why bother investigate sound at all, really? And for this, I can borrow really from the reasons for incorporating a microphone speaker into the V2 in the first place. And that's that sound vastly expands the range of applications the V2 can be used for, and the academic subjects it can be used to enhance. And as we've seen throughout the event today, there's loads and loads of things that you won't even think about it can be useful. Sound is interactive, it's tangible, it's engaging, and most importantly, it's fun. And children are just really naturally drawn to it, and they just want to play with the sound as soon as they know it's in there. So for any teachers listening, I apologize. But foremost, the Microbit was obviously an educational device. So, kind of, what are the benefits of sound in this area? What can it bring? And these are the things that I kind of proposed, and these are the things that we'll look at the end. Were these achieved in this kind of project? The main advantage of sound is that it can break down these kind of traditionally black box concepts, or a concept that you can't physically represent or see. So internet messaging is a good example of this. You can't see them, you can't smell them. They're invisible things, right? And you can use sound to represent these in a much more tangible and understandable format. And you can use that to kind of, well, the term we're using is a stepping stone to these more advanced kind of radio features by learning the basics in a more tangible, real-world example using sound. Additionally, hopefully this is going to help to go some way to improve accessibility of the device, especially for people with visual impairments, as part of that kind of ongoing process. Okay, so these are all the kind of great features of sound, and we've got the hardware on the V2 with the inbuilt microphone and speaker. The question is, how do we kind of really squeeze out as much value as we can from these new features, and how do we extend them? And then to frequency recognition. So after brainstorming a bunch of options to kind of how do we expand on these sound features with the Microbit, I chose to look at frequency recognition because it carried on quite nicely from my placement work, which was making sound. And also it sounded the most fun to annoy my housemates with, which I'm sure they were very grateful for. So yeah, like I said, the Microbit is quite good at making sounds at the minute, as I'm sure any of you have played with it will know. But it doesn't really do much in the way of recognizing sound, and that kind of feels like kind of a natural way to complete that circle: recognize sound, produce sound, recognize sound, produce sound. So what are the main questions I was kind of looking at and answering in this work? Firstly, is frequency recognition even possible on the Microbit V2? And spoiler alert, good for me that it is, or else this would be a much shorter presentation. We also ask, how accurate can that be? Is it just there is a sound playing, or can you narrow it down to a specific note? What types of sound can be recognized? So obviously, a sound played from the Microbit's inbuilt speaker will sound different to a sound played on a phone or a computer, or even a real instrument. And finally, of course, even if it does work, is it actually any good in an educational context? Okay, before I get you guys talking, just briefly, what actually is frequency recognition? Well, it's as simple as the kind of word suggests. It's getting what the microphone hears and turning it into a frequency, which we measure in hertz. And that can be translated into a letter note if you want to. So you can see there on that little table, the letter notes, which you're perhaps more used to, C, D, E, A, and they all have this hertz, which is actually related to the wavelength, but that's too technical and boring. So basically it's listen to the microphone and see what note's playing. Okay, so now you know a little bit about frequency recognition. And before I reveal some of the ideas that we kind of envision this would be useful for, I'd like you all to take a minute, the guys in the audience, and see if you guys can come up with something or a project or something fun which might use frequency recognition. And I'd like to see what kind of ideas you've got before we really get into it. So I'll give you one to kick off, perhaps a guitar tuner. There's one that we came up with. So you could imagine if your microbit could determine different notes, you could strap it onto the top of your guitar and see when it was in tune, and make your own guitar tuner. So I'll give you guys a couple of minutes just to try and pop your ideas in chat, and we'll have a look at what you guys come up with. And you can do the work for me. That'd be better. So yeah, I'll give you guys a couple of minutes and I can drink some water. And get my demo ready for later. Okay. Awesome. Okay, let's have a look what you guys have come up with. I can see the chat. Aha, harmonize with singers. Yeah. That's a nice one. I'm sure it would be much better used on somebody who could sing, unlike me. I did consider this, but I thought, yeah, me singing, not something I want to subject you guys to. But it makes me think of that. There was definitely a game, right? It's like SingStar or something, and you have to sing along to the notes. Yeah, I thought that'd be quite cool if you could make your own one of them, right? Graphic equalizers, yeah, definitely. That would be cool when you can imagine them kind of dancing along. Cool. Yeah, data transmission. We did something similar with the Fireflies project, right? With radio, you could kind of represent that as with sound. Yeah. Oh, yeah, and using it as a trigger. So we'll get on to kind of the different ways you could detect a frequency a little bit later. So all excellent ideas. Thank you for that, guys. And I shall add them to my word cloud, which you can see I've slowly been building as people have given feedback. So yeah, you've got a lot of these kind of communication and networking, radio, Morse code you could use to represent these things. You've got physicsy stuff, Doppler effect, and the speed of sound, that kind of stuff. Music, singing, pitch detection, measuring the kind of music reactive stuff, or automatic metronomes that sync to your beat. So yeah, it's okay if nothing's coming to you straight away. It'll be one of them things that you kind of think about on overnight, and you'll think of some things at 3 a.m. and have to rush up and write them down for me. Okay, so thanks for that, guys. And we'll carry on. What does the system that kind of can do all this look like? And these are the objectives that I set. There's kind of 3 main categories. Obviously, we've got the technical challenge of, can we actually detect accurately within about a hertz, probably, if you wanted to do kind of instrument tuners, kind can we do that? You've got obviously the educational value, which we've mentioned. Is it able to deliver new areas of the curriculum? And are we able to make currently difficult concepts easier? Because if it makes them harder, there's no point. And obviously, in order to be successful, we've got to consider the usability, and we've got to consider the audience. It needs to be engaging, it needs to be appealing and easy to use for our kind of target audience of late primary school, early high school. So just before we jump in any further, we should probably start to consider why the microbit's so good for this project. There's kind of obviously two major competitors with Arduino and Raspberry. But despite these companies making a huge range of products, the Macrobot V2 stands out as the clear winner for a number of reasons. Firstly, it's got a huge existing presence in schools already, with over 20 million children already learning with the microbit. For the price point of £10 to £15, the hardware is better or competitive at least with the rivals. And perhaps most importantly for this work, none of the other competitors have a board which has a built-in microphone and speaker. So you have to have extra components, wires, soldering, whereas the microbit's just kind of ready to go out of the box. On the software side, the microbit's got it covered as well. So obviously it can be programmed in anything from C++ to Python to make code. So it really is quite a good package for this piece of work. Okay, so how does it work? I won't bore you too much with this. If anyone's interested in the kind of nitty-gritty bits, then feel free to reach out to me after. But for the most part, I imagine this will be very boring for you all. So here's a high-level idea. Basically, we take in time domain information from the microphone, which is this red squiggly line you can see. And we use a process called FFT, or the fast Fourier transform algorithm, to convert that into a frequency space. So what we do is we take that wiggly red line and we want to split it into its pure sine wave components. So there might be just one, if it's quite simple, if you're just playing one note. If you're playing more than one note, like a chord on a piano, there'll obviously be more. And this algorithm basically spits out this graph, this blue graph, which shows you the peaks in frequency, and they are the kind of frequencies that it's detecting. So what does this look like? And what does this look like for different note types? So sine waves are quite easy to detect. I'll show you what they look like, and I imagine nobody will have any difficulty recognizing which frequency is detected there. That one very obvious large peak on the graph. Unfortunately, the microbit primarily uses square waves, and square waves, when you put them through an FFT, look something more like that. Now, 10 points if anyone can tell me which of them spikes is actually the frequency we wanted. I'll give you a second. 10 points, anybody? No, it's a trick question. It's none of them. It's actually the distance in between the spikes that we want to find out. So this is another challenge when looking into this area, because it's not quite as simple as the sine waves. And obviously this is in the perfect world. So if we look over into the real world now, what do we actually get from the blue FFT graph when we play a note to it from the microbit? Yeah, it's starting to look less pretty. We have these kind of double spikes now. They're kind of all out of order. There's different sizes. And this was kind of the core problem that we kind of have to overcome with this dissertation, especially if you start to play more than one note at once, because it starts to look more like that. So really the main kind of time was spent taking that graph and that information and trying to produce these component frequencies that we want to detect. Okay, so what did this developed system actually end up being able to do? So as somebody mentioned with the triggers, yeah, we've got the event here. So we said, if you hear an A or an E, then do something, and then we have this idea of primary and secondary notes. And basically they're just determined on volume. So primary note is the loudest note that it can hear. And the secondary one is if you're playing another note at the same time, the second loudest one. So if you were playing 4 notes, it would pick the top 2 in terms of loudness. If you weren't playing, if you're just playing 1, you just have a primary output here. So yeah, we were able to get the closest primary note. That's the letter, so A, B, C, D, and actually get the primary frequency, which was in hertz. So you could, make it easier and use the notes, or you could dive a bit deeper if you wanted and actually start getting into hertz and wavelengths. Okay, so once the system was all up and running, how do we evaluate it? So there's 3 stages to this evaluation I did. First, it was obviously the internal testing, which is all that kind of boring quantitative stuff, how far can it recognize, what range of notes can it recognize, and how well does it technically perform. And then you've got the qualitative kind of stuff, which was really looking, can it achieve them educational aims we highlighted at the start of this presentation? Does it allow you to create programs which can kind of break down them black box concepts? Can it enhance the learning experience? So here we go, what we've all been waiting for, the results. Was this dissertation actually worth it? Well, firstly, how accurate was the recognition, and can we detect them from phones which use the sine waves and from other microbits which use their more difficult square wave looking ones? And the result is, thankfully, yes, we can, and actually with surprising accuracy. So across the board here, we can see there was an average distance between what we actually expected, so the true note we played, to what the microbit said it was hearing, what it detected, was just 0.7 hertz out. And for scale, you can see between each letter note, so the distance between an A and a B, is something around 30 to 50 hertz. So being 0.7 of a hertz is pretty close, and it's in that kind of ballpark of being able to do instrument tuners and that kind of stuff. So what distance were we able to recognize these notes from using this FFT? Using a microbit speaker, which obviously isn't super loud, we were able to get notes recognized from 90 centimeters for all of them. Some were a little bit further, but all of them were at 90 centimeters. So it's quite a long recognition distance of just under a meter. And obviously, if you use a phone or a bigger speaker, you could kind of pump this distance up. But that was just using the inbuilt speaker and inbuilt microphone of 2 different microbits. Did it work on live instruments? Well, again, live instruments are a tricky beast. If you look in this little diagram at the bottom, this is a true C played from a tuning fork, and this is a C played in a clarinet and a trumpet, and what them waves look like. And you can see they're quite messy and difficult. So surprisingly, this did manage to work. And although we had a few problems with what's called concert pitch, so for example, a trumpet, if you play a C, will actually come out as a B flat because that's how they're tuned. So we'd have to make a slight adjustment for what instrument you were playing. But with them adjustments made, it was certainly plausible that this detection would work with real instruments. We tried it with a trumpet, a saxophone, and a flute, and they all worked. Just some were slightly off with this tuning pitch. But yeah, it's certainly reasonable to say that it would work with real instruments too, and not just electronic sounds. For anyone that loves some numbers, here you go. The developed prototype system was able to theoretically recognize frequencies from 0 to 5,512 hertz, but you probably don't really want to be going over 2,000 for a human anyway. And the maximum error was about 5.38 hertz. So towards the top and bottom end of them scales, it's not quite as accurate, but we didn't really test the whole range. It takes 10 to 11 milliseconds to do that processing. So from the time it says, right, go listen, 10, 11 milliseconds before you get a result. So really pretty quick. So certainly fast enough to do close to real-time processing with this. Okay, so technically it kind of works. What did people think of it though? Does it work in an academic system? Well, here's what they had to say. They said it was kind of accurate beyond what they thought it was going to be. The academics thought They really like the portability of the microbit, which is what I was kind of saying with that versus competitors thing, right? It's really good because it's just a whole package. You don't have to worry about extra wires, extra components, extra bits. They thought it enabled difficult concepts to be presented in a way that's much easier to understand. So that's great. They thought the features were engaging and fun, that it widened the appeal of the microbit to people who perhaps wouldn't otherwise be interested. So you're thinking here people who perhaps are interested in music, who might not traditionally be interested in computing, and this is kind of a route in for them. And they concluded it kind of did open up a lot of new projects, lessons and topics that could now be explored that previously couldn't. So things like the Doppler effect, things like that. The second one, the second trial was with the Macrobot team themselves. So unlike the first one, which was a blind test, so they really got to see kind of their first impressions of it. Obviously, the Macrobot team were collaborating on me with this, so they knew all about the squeaky, horrible sounds it was making. But yeah, they were also impressed with the kind of accuracy of the detection and the distance it could be recognized from. They thought it was useful for teaching these black box concepts, and then that would allow a deeper understanding to be gained by the kids. They thought it was much more appealing than radio specifically, and it's quite easy to draw parallels between sound and radio, which we'll see in a few demos in just a short while. They said it was more engaging, appeals a wider audience, and it improves accessibility. Anyone can join in by singing, humming, and also on the visual impairments, you can improve them, but I won't demonstrate that to you now, as I previously mentioned. Again, yeah, they managed to identify a lot of use cases across a broad range of subjects, a lot of which you saw in that sound, in that word cloud just previous. Okay, so what's the conclusion? Was this worth doing? Well, we found sound recognition is possible, and it's accurate within about 1 Hertz. Recognition can be done with sine waves and from square waves, like the microbit's own speaker, and also from real instruments. In terms of having educational value, well, yes, the new features allow the test users to create new systems that widen the range of topics that could be taught with a microbit. The teachers concluded it made teaching currently difficult black box concepts easier by making the method of teaching more transparent and more tangible, physical. That's things like the internet messaging. And it was agreed the features were engaging and fun, and they improved accessibility. So to round all that up, what did we learn? Well, we learned accurate frequency detection of multiple key frequencies from a range of devices and instruments as possible on the Microbit V2, and also that there is educational value in extending the sound features of V2, which are all the benefits we mentioned at the start. And frequency recognition is one suitable way in which to do this, and obviously I'm sure there'll be many more as well. So there's still plenty of work to do on this. The UI, which we'll see in a minute, was flagged for improvement. We could increase the range of letter notes that can be shown. So currently we're only able to detect the middle octaves, so C4 and up. The number of concurrent notes, when we have that primary and secondary idea, is obviously limited to 2. And it would be better if you could kind of recognize 3, 4, or 5 notes at the same time if you're thinking about doing chords on a piano. Extra statistics would be good. So if anyone's used the radio, you'll know you can get statistics from it, like the signal strength, which would obviously be volume in our case. And the last thing to consider, although the teachers who tested it didn't flag this particularly as an issue, lots of sound in a classroom, especially high-pitched ones, could be quite annoying. And how do we kind of go about mitigating that if it does turn out to be a problem? Okay, that's enough waffling on. Let's get into the fun stuff. So I'll give you some quick demos here of the system that I've been working on about, and you can see how it actually works and what it looks like. So we're going to try a live demo. Fingers crossed, this will always go well, won't it? To start with. So can somebody give me a frequency between kind of 100 and 550 hertz? And I'll show you a little bit what this looks like. Which you can just pop that in the chat. 240, excellent choice. So I'm just going to go on a tone generator on my phone. I'm going to type in 240 hertz. So you can see that's now making that sound. If we look, I'm not sure how well you're going to be able to see this. Let me try and make it a bit bigger for you. So here we have this format. It's a little bit confusing, but here we go. Primary note, secondary note. This X will tell us if it's a letter that's heard, and X means no letter. And this number is what we're really looking at. That's the frequency that it's picking up. So we're only playing one frequency, so we're just interested in the primary notes. Let's see if it will recognize the 240 when we start playing it. Not bad, 241. Yeah, a bit of rounding error, we can take that. So I'll show you now, we can play C. And I'll just go up through the scale. That's a D. An E. F. And G. There's an A. And finally a B. So that's the kind of raw output that we can get from the microbit. And thank goodness that worked. Okay, so now I'll show you, that's kind of, like I say, the raw, bare bones kind of functionality that this system provides. But what can that actually do? How do you use that? So I've given some, I've kind of come up with some quick demos to show how that could be used. And these are the kind of demos that I gave in them user trials to get the feedback on it. So the first one we have here is HTTP request response. So this is if you were teaching about web development or something like that. How do you physically demonstrate an internet message, right? Really, so it's quite a basic thing, but how do you teach that, right? You can't see it, you can't feel it. Well, this is one way you could do it with sound. So this demo shows signal strength. So these two microbits are bleeping to each other. One plays an A, one plays an E. And it's just a super simple logic. If you hear an E, play an A. The other one, if I hear an A, play an E. And they'll just talk to each other. And basically, I'll move them apart, and you'll see how that signal strength, or volume in our case, diminishes, and they start to get weaker, and eventually they'll stop talking to each other. And this is how we can kind of represent communication in this sound form. So I apologize if anyone's got any dogs, because there's going to be some beepy sounds. Here you go. Now you can see they've stopped. So the volume wasn't loud enough to be detected anymore, and hence the message has failed. So just one example. Here's another one, a good one, noise. How does noise affect a signal? So obviously in the real world, we get interference from other things. That's why your TV remote doesn't work or something. And you can actually represent noise in this format with real life noise. So again, these two microbits are just talking to each other, beep, 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 beep. And you can see when I make a lot of noise by tapping the table, then the messages will fail, just like a packet would fail in a network if there was too much noise. There we go. Okay, yeah, this one is just showing you. So we did with a phone then in the live demo. So this is a microbit actually making them sounds, which it can already do. So the one with the black cable is making the sounds, and the one with the white cable is actually running this system that I built, and it's going to display on the screen which note it thinks it's hearing. The note displayed on the one with the black cable is what we're playing, so hopefully they should match. And there we go. So that's what it looks like microbit to microbit. And obviously that's a super simple demo, but it just shows the functionality of. Okay, there's one last one I'll show you, and then we'll go through some questions. And that is some Morse code. Here we go. So it's a little bit slow, but here's actually one playing Morse code. The one with the black wire is playing the Morse code out, and the one with the white wire is displaying the letters that it hears. So it's going to play A, B, C, D, E, F. And hopefully the one on the left will pick that up. So this is representing communication through sound. And there we go. I think the sound was a little bit out of sync on that one, but yeah, you can see the right one was sending them little beepies, and the left one successfully recognized that Morse code, and it converted that into a letter. Okay, so that's it from me. I'll stop boring you now. Yeah, here's any kind of questions, fire away. Again, if you're interested in stuff, just find me an email. It's absolutely no problem. There you go. Thank you very much.
Hey, Joshua, amazing job. Thank you so much for that. And especially the demos. I really enjoyed actually seeing it happen, which is exciting. We have a question from Tanya that said that you mentioned this as part of your dissertation. Is a copy available for general consumption?
Yeah, I can definitely get that to you. It's not published anywhere at the minute, but yeah, if you pop me an email on the screen there, yeah, I can send that over to you if you'd be interested.
Awesome.
It is a big read, though. I'll warn you for that. I think it's 70,000+ words.
That's a good dissertation.
Yeah.
Martina's asking, will this become an extension in Make Code?
Well, there is a lot of work that's kind of close to doing it. I'll show you. The UI is built in Make Code.
Same asking if it's like it's available in GitHub.
But, yeah, I think the work is available in GitHub. I'll check with you. I'll check with that and get back to you on that. There we go. So you can see, slowly loading. My internet's not brilliant here in poor old Stoke. Here we go. There we go. It's waking up. So yeah, I have built them in Make Code. So here are the blocks you can see, which I've got the kind of event blocks and the kind of on hearing blocks and stuff. It does use a kind of special version of the Make Code runtime now. So I'll look into how you guys can kind of play with it yourselves if that's something you're interested in.
Perfect. And you could actually just even post it in the event chat if you do find it, if this chat closes down. We are at time and we are now moving into our next sessions. So once again, thank you, Joshua, so much. And just also, you should be very proud of the work that you're doing, especially for your master's. And I don't think it needs to sound any more exciting than it is. So it is fantastic.
Thank you.
Thank you so much. And everybody else, us. We will move on. If you go back to your sessions tab, we have sessions coming, interactive sessions once again. So let's get to it. Thank you.
All right. Thanks so much. Thanks, guys.
Bye.